Great, thank you. Very fun to be back here, and fun to be seeing Bill again in a very different setting. Okay. So today I will be talking about environmental flows and how to integrate environmental flow into policy and water management. And the basic outline of the talk is I'll first set the stage by talking about concepts of hydrological alteration and the implications of that, and how this concept of environmental flows has evolved over time to address the issues of hydrological alteration, and present a hierarchical framework that the Nature Conservancy has been working on to develop environmental flows and to make environmental flow recommendations. And then finally taking the next step, which is trying to integrate these flow recommendations into actual policy or management, which is the true challenge of this field. Okay, so if you look at this slide, which shows the proportion of U.S. species of different taxonomic groups that are at risk of extinction or declining populations, what would stand out to you? What pattern or trend would stand out? And that really they are all aquatic species. And this is something that really comes as a surprise to a lot of people, because they're sort of off the radar screen for a lot of people. And maybe it's because they are literally under the surface of the water and difficult to see. But a lot of people, when they think about endangered species, they think about either larger and charismatic animals or just terrestrial species in general, the rainforest. But actually the rates of impairment and extinction in freshwater ecosystems are greater than for terrestrial and greater for even the high-profile terrestrial habitats like the rainforest. So there's great endangerment. And then the other surprise for a lot of people is that when people think about problems with rivers and problems with lakes, they almost always think about pollution. So it's a water quality issue is what comes to mind for most people. And that certainly is true in some places, and it certainly is a causal factor. But one of the leading causes of decline for species, and in this country in particular, as we've made great advances in water quality, a leading cause of decline of species is hydrological alteration. And that means changing the way that flows move through a river, the timing, the magnitude, removing the floods or changing the low flows, just different ways that we manipulate the water system in terms of how water moves through the natural system. And of course that can be done by dams that store water, regulate flows, and also through the loss of connectivity as levees and flood walls prevent rivers from reaching their floodplains or riparian habitats. That is also a form of hydrological alteration because it changes the way that the natural flow regime interacts with the river channels and the riparian habitats. And this just shows to show the ubiquity. Is this actually moving? Let's see. Oh shoot. Okay, there's something interesting about this slide that's not happening. And I can't figure out why, because I've tested it and it works, and then it doesn't work. And it's nervous, I think. It gets very nervous. But anyway, what happens is this says before 1750, and there's just a couple red dots up there in Spain. Spain was leading the way in building large dams. And the great visual effect that you should be seeing is that by the year 2000, there are red dots just covering the earth. And there are, and it actually is only showing 23,000 of the large dams worldwide, but there are estimated to be 45,000. In fact, let me just do something more quickly just to show that, because that is really interesting. No. Okay, I don't know why it worked. Maybe it's a computer issue. Okay, so this is another way of looking at the end result of all of that dam construction that has happened. And this shows hydrological alteration and fragmentation of rivers. So the rivers that have been dammed up and had their natural flow patterns affected. And you can see that for most of the most of the industrialized world, in Europe and North America, it's colored red, which is the most fragmented basins. And then there are a few parts of the world left that are green, which is relatively low fragmentation, low hydrological alteration. And then a lot of the world that's in this yellow. But this really shows that it's fairly ubiquitous, the hydrological alteration. And that explains why aquatic ecosystems are in such peril. And so to address this, over the past several decades, the concept of environmental flows has been evolving. And environmental flows can be defined as the flow of water in a natural river or lake that sustains healthy ecosystems and the goods and services that humans derive from them. And that latter part is a really important thing to emphasize as well, because those slides that talked about aquatic biodiversity, that is certainly a major issue and something that we think about. But also, these freshwater ecosystems provide an immense amount of what are called ecosystem services to local communities, to regions. For example, in the Mekong River, there are millions of people that depend directly on the fisheries. It's the world's most productive freshwater fishery. And there are millions of people in Vietnam and Laos and in Thailand that depend on that river. And that river's fishery is largely maintained by a natural flow regime. That natural flow regime allows the river to move out onto the floodplain where the productivity is at the highest, and that produces massive fish production that supports that. And the Missouri River used to be an extremely productive freshwater inland fishery, but basically since the hydrological regime has been so altered, it's no longer providing that. So it's not just thinking about aquatic biodiversity, it's also really important to think about the communities and the regions that depend on the goods and services that these naturally functioning rivers provide. In environmental flows, the concept is really, initially people talked about minimum flows, then they began to talk about in-stream flows, and now more and more people talk about environmental flows. And I'll get to that evolution in just a second. And there's an amazing range of methods to try and determine what an environmental flow should be in a river. A recent survey in the literature found more than 200 different methods, and they range from very simple to very complex. And so water managers and agencies, decision makers are very frequently looking for guidance. Well, what should we pick? What method should we pick? What's going to give us the best answer? And so much of my talk is going to focus on how the Nature Conservancy would address a question like that. So there's these basic categories of environmental flow methods, which I really am not going to get into very much, but they range from being more simple, the hydrologic, all the way down to more complex, called holistic. And I won't get into these too much, just that these are the four main categories that those 200 different methods can sort out into. But environmental flows, the reason that they have evolved from the concept of minimum flows to in-stream flows to environmental flows is the concepts of the natural flow paradigm, which research was really looking into in the 80s and 90s and was most effectively articulated in a paper in 1997 that coined the phrase the natural flow paradigm. And it held that there are 5 primary factors that influence the way ecosystems respond to a river's flow regime. And that's the magnitude or the amount of water, the frequency of different events, the frequency of floods or the frequency of low droughts or low flow events, the duration. A flood that lasts a day is very different than a flood pulse that might last 2 months in terms of how fish will respond to that flood event. The season, so certain trees release their seeds to coincide with floods, and that's effective if it happens in a springtime flood, but they're not releasing their seeds in the fall. And then rates of change. And this picture just shows how you've got your low flows, but really this pool that you saw before, it's created during these high flow events. And so if you only think about the minimum flows and maintaining enough flows to keep fish alive, which is what minimum flows often are intended to do, you're missing out on these other parts of the variable hydrological regime that actually create the physical habitat during the flood events. And then after the floods recede, they create these holes and these pools that they leave behind these pools that are the refugia for fish during the very dry periods. And so most of these methods that were being very commonly used by agencies to try and set environmental flows or in-stream flows, they would often seek a single or just a few discharge values or flow values. And either that was inherent in the method the method itself just simply tried to find one flow value, or it was how the method was generally implemented, that for simplicity's sake, people tended to just seek a couple different flow levels and have that be the answer. But one or a couple different flow levels was very difficult to reconcile with our growing understanding of how functional riverine and riparian ecosystems worked in terms of the flow regime. And so I feel like these pictures can really illustrate how this concept of environmental flows has been evolving. Is that originally it really focused on stable low flows, minimum flows, maintaining enough water in the river, versus what we try and talk about now, which is a range of different flows, including floods. In-stream flows, which literally are in the stream, in the channel, as opposed to flows that get out of the channel and get out onto the floodplain or get out into the riparian corridor. And lots of research in the past 20 years has shown how important that can be. Very much focused on trout. A lot of the methods were focused on identifying what would maintain trout fisheries, whereas now these methods are trying to be more comprehensive and looking at riparian vegetation and sediment transport, large wood and channel morphology, invertebrates, the whole basis of the food web, and also people, thinking about how people use these systems, either for recreation or for subsistence in a lot of the world, or for, in a major sense, in terms of commercial fisheries like the Mekong. Whereas previous, really, they focused on people, but mostly people catching trout. So it was a little bit simpler approach. And I don't want to minimize the efforts that were made in terms of the 1970s to really focus on minimum flows and in-stream flows, because just getting those accomplished in a lot of places was a really big event. And clearly, a river with no water is going to collapse entirely. And so just there was they really were setting the stage by doing what they did to get these concepts that water, a certain amount of water should be in a river. Just getting that concept on the table really did set the stage for thinking more broadly about environmental flows. And then I'm going to focus on holistic methods, which those were one of the four, hydrologic and hydraulic, and holistic is one of the four. It was originally developed, one of the four methods for how you set environmental flows or determine environmental flows for a river. It was originally developed in South Africa and Australia, and it was initially for places where there were very few data, very few studies that could really tell you much of anything. And so it was largely, it would draw upon expert judgments and bringing together a group of people to think through and look at the river and make hypotheses and draw from a range of disciplines. And it explicitly looked at variability in terms of different types of flows, and it explicitly looked at a range of resource values, not just fish, but riparian vegetation and sediment transport and invertebrates, a whole range of resources that make the river ecosystem. And I'm going to use this holistic method as a foundation for a framework that we've been using to think about environmental flows for situations that range from being very data poor and resource poor to being very data rich and resource rich. But this holistic approach is one that really should be infused into any of those approaches. And that the basics being thinking about a range of flows, a range of flow types, not just minimums, but thinking about high flows, low flows, and thinking about a range of resources. And if those two underpin the approach, I would maintain that you could call that a holistic approach, even if it's relatively simple. And speaking of relatively simple, what I mean is you can do these what are called hydrological desktop methods that basically are just collecting available data and running some models and some analyses and getting a first cut picture of how that river ecosystem works. But if you do that, thinking about variability and thinking about a broad range of ecosystem processes, that could be considered a holistic approach because you are explicitly considering all those things. And so I'll call that like the level 1 approach. And then level 2 is this expert panel approach. And that really is what originally was called the holistic method in South Africa. And that's where, in situations where you don't have very much data, you can bring together a group of people from multiple disciplines and try and think through and come up with some first cut recommendations for how that river should be managed. And then what's level 3 is much more complex methods that integrate a range of tools, including some of these are what people would call an environmental flow method, like a standalone method, like this, what's called PHAB-SIM, the Physical Habitat Simulation Model. A lot of people, that would be used as just a straightforward, you use that one tool to set an environmental flow. Whereas in this context, you might draw upon that as one of your tools, but it won't be your only tool. You will draw upon a whole range of tools and methods and approaches to try and look at that variability of flow and that range of resources. And this could be thought of that you look at your resources available in terms of funding and time and data. And if you have very limited, then you can do this hydrological desktop analysis. If you have a moderate amount of resources, enough to bring a group of people together, do the expert panel approach. And if you have extensive resources, you can do this holistic approach that incorporates field studies, modeling, and all those different, picking and choosing from all those different methods. But I actually think, and then, I'm sorry, I should have mentioned this, and then what we consider to be level 4, that any of these are actually moving towards, is adaptive refinement. And I'm sure at Duke, at school here, you hear a lot about adaptive management, and so that's a very common concept, and perhaps overused concept, but it's an important one to think about, particularly in these places where we don't have that much information. So if you set environmental flow recommendations, it's very important that there's a monitoring program that will actually test and refine those recommendations over time. But rather than thinking about those as initial choices, I think it's more useful to think about them as sequential implementation, starting with that hydrological analysis that gives you just the first cut of what is the variability and what is the hydrological regime of this river system and how has it been changed. And then bringing people together to develop conceptual models, develop hypotheses, just bringing in a range of stakeholders and using that to guide the next step, level 3. So if you are going to deploy more serious resources, financial resources to do field studies and modeling, that it is guided by the stakeholder and interdisciplinary process that preceded it. And so this could be a sequential process that builds on itself. And so quickly, just to talk about these different methods, the hydrologic desktop method it could be either the first step that precedes the other steps or a precautionary standalone approach if there aren't any further resources. And the Nature Conservancy has developed a software tool called the Indicators of Hydrological Alteration, IHA, which can be used as one of there are other models as well that can be used, but this is one that can be used to analyze the flow regime of a river and to begin to look at the natural patterns of variability, and then linking that with just basic understanding of river ecology and literature sources or anything else you can get your hands on, you can begin to get an idea, a picture of how that river is functioning. This slide shows the output of that IHA software, and it basically looks at a hydrological data set and compares. You can use it to either just get the basic statistics. It generates 67 statistics about hydrological variability, and that can either just be an analysis of a river system, or if you know that river system has been altered at some point. For example, this shows where a dam was built in 1963, and so you see the range of variability before and the range of variability after the dam was built, and that flows in generally decreased. And so if you look at this for a whole range of different variables, you can begin to zoom in on what are the most important, and if you link that with the understandings of riverine ecology, you can begin to generate the first set of hypotheses about what is most important in that river, and also a first set of recommendations of what might be important to maintain. Then the next level is this expert panel approach, and so that really is drawing upon the expert judgment of an interdisciplinary group. It was originally, this approach was developed in Australia and South Africa, and I'll illustrate it with an example that the Nature Conservancy did for the Savannah River in collaboration with the U.S. Army Corps of Engineers. So this is the Savannah River with J. Strong Thurman Dam and a diversion dam above the city of Augusta. And then below the city of Augusta is a long stretch of river with a fairly intact floodplain, a very wide bottomland floodplain forest, very rich in biodiversity, and then a very important estuary that supports commercial fisheries. And the Army Corps of Engineers controls the flow of this river through their upstream dams, and they manage these dams for flood control and for hydropower primarily. And the Army Corps was as part of a comprehensive study looking at other resources in the basin, was interested in looking at the flow regime. And so the Corps worked with the Nature Conservancy to bring in about 45 scientists from academia, various state agencies and federal agencies, the private sector, and they just got them into a room and worked through what was known about the Savannah River. And they, through this process, developed these conceptual models of how the flow regime related to the different life histories of important organisms, fish and reproduction of trees, and just began developing these conceptual models, and then they broke into working groups. So a working group on fish, a working group on trees, a working group on the estuary, and developed a set of recommendations for different types of flows that would be important to maintain or reintroduce into the system, including low flows, high flow pulses, and floods. And these recommendations were divided into wet years, average years, and dry years. So these recommendations would be different depending on the year type that you were in. And because these were not based on detailed modeling or studies, these were really framed as hypotheses. It was hypothesized that a flow of 20,000 to 40,000 cubic feet per second for 2 to 3 days once per month in this time frame, in the late winter, early spring, would be important for dispersing tree seeds and for moving large wood into the channel and for giving fish access to the floodplain. But maybe it's not 20 to 40,000 CFS. Maybe it actually starts at 18,000, or maybe it takes 50,000. That's the kind of thing that you would monitor, study, maybe commission a study to do hydraulic modeling to actually understand what flow level would allow these processes to occur. So these were framed as hypotheses, and so it's really, these are not set in stone. It's, through monitoring, research, and adaptive management, these hypotheses and recommendations can be tested and refined. And this is an example on a project that I worked on in the Willamette River, just to show what a recommended hydrograph might look like that comes out of one of these processes. This shows the different flow components with their associated linkages with the ecosystem, and then this kind of integrates that into a hydrograph, an actual hydrograph that would meet those suggested flow components. And it's a little confusing at first, but the blue line shows the natural flow. That's what's happening in nature. The light red line, like here, shows how the river is currently managed. Where the red line is thick, it shows where the recommendation and the current management approach line up fine. So it wouldn't require any changes. So this red line is basically what they're doing currently, and where it's thick, it matches up with the recommendation. The green line is where, to meet the recommendation, there would have to be some change to the flow release. And that's where you see that this dotted red line departs from the green line. So taking a step back, the thick line represents the recommended hydrograph, with the color red indicating what is already occurring, the color green indicating what would need to be added to this hydrograph. And then for comparison, you can see that there are various peaks and floods that are happening in the natural hydrograph that the environmental flow recommendation isn't saying you don't have to have every flood. It's saying you need to have 2 floods in a wet year, and that's what you see, the creation of in-stream and floodplain habitat. And then for cottonwood regeneration, you need this particular rate of change that you see being drawn in here. So the managed hydrograph drops far too quickly, and so that is something that we would then take to the dam operators and see which of these components we can add back in. And clearly there are some that are easier to add back in than others, and we'll get to that. And so this is the basic process for this expert panel approach. This orientation meeting, and it's really important because that is bringing all the stakeholders together. And so it's not just a scientific process, it's a social process. And whatever comes out of this will be much more durable if it has a broader-based participation. And then a review and summary report is just pulling together all the information that's available for the system, including doing a hydrologic desktop type analysis to just look at the variability in the system, And then the real heart of it is the flow recommendation workshop. And so all the people coming here have the information that's been synthesized here, and they develop these conceptual models and hypotheses that can be translated into recommendations. And then in step 4, in the case of working with the Army Corps of Engineers, you take those recommendations and you work with the dam operators to see which of those flows can actually be accomplished. And some they can do right away. Some they say that's fine. We have the authority or the ability to manage somewhat differently. And some would take either a legislative intervention to allow them to do it, or a physical intervention in terms of the structure of the dam itself or downstream land use, and then implementing these flows and studying and learning from them. Also using this as a springboard to generate the kind of funding and support that you might need to do these research methods that will allow you to refine and improve on your recommendations. And so at this step, the recommendations are they're based on a synthesis, a review, and expert judgment. But that probably isn't going to suffice for the Corps in terms of, they're not going to release a high flow unless they're pretty darn sure that it's not going to flood a city. So that's when you clearly will need to raise enough money to be able to do hydraulic modeling and those kind of things that will allow you to see if those flows can be implemented. So that's why this is really an iterative approach. And then level 3 really just builds off on what I was just talking about this being an iterative approach. Level 3, in some ways, is just level 2 where you have a lot more money up front. And that situation definitely arises. In California, it has arisen in part because the system in California is so complex and so fraught with conflict, endangered species that are affecting the way that the water supply system is managed, and you've got billions of dollars of agriculture in all of Southern California dependent upon decisions. And so therefore, there is an awful lot of money in play. And so the example that will show how an approach was taken in California that had all these resources up front. But what we would suggest is that you can follow the same basic approach even if you have all these resources up front to do more sophisticated research and modeling, because of how critical it is to get the social part right, to get the stakeholders involved, to get a more durable process, and also because just to ensure that the scientific process doesn't go off on its own without a more without the input of a broad range of disciplines and a broad range of stakeholders, to ensure that research process is focused and addressing the most important questions. So how we would suggest changing that basic flow is that rather than having a workshop that generates flow recommendations, the workshop is generating scenarios and questions to test. It really is like a first cut, but it's more of a guidance process for the research program. And then the research program takes off in step 4, and it is deploying, these are just some examples. It can be, any of these or others, but a meander migration model, or a hydraulic model, or a population model, population viability, or a temperature model. But this step 3 has really guided those decisions to make sure that they are using the resources and the science most effectively to address the most important questions. And then analysis of all that research, and again, bringing it back now to step 6 to basically have a flow recommendation workshop, because these models and research approaches aren't going to give you an answer. An answer still requires some sort of synthesis and some sort of dialogue between different groups to actually come up with some sort of recommendation. And that's where, again, it's important to have a process where you have people involved from a range of stakeholders and a range of disciplines. And this just illustrates how you can use different models to address different parts of a hydrograph. And so in a system where you have salmon, you might be concerned about fish passage when they're moving upstream. So you do a fish passage model that looks at barriers and what flows they need to get over barriers. Maybe temperature is the critical thing over the summer. So you do some temperature models. What kind of flow do you need to maintain 68 degrees for salmon? And if you have cottonwoods in the system, well, maybe they need a certain recession limb on that hydrograph. And you're picking and choosing from different, through this process has guided you to which research methods and models to use to put together a hydrograph that will then be able to meet these different things. So it's synthesizing one hydrograph from a range of different tools and not relying on a single tool to give you a single answer. And this is this example that I alluded to from California. You've got these focal species, several of which are on the endangered species list, so it has regulatory consequences. And these species have a lot of data and models that already existed for them. And the Nature Conservancy, working with state and federal agencies, raised significant funding to do a flow modeling and flow recommendation exercise that would be able to answer questions about how different flow regimes affected these species. And through this, they were able to commission new research, new models, new field data to calibrate those models. So it was a very resource-intensive process. But they did it through that process that I described earlier, bringing together a group of people, having those people synthesize what was known, and having that guide the most important questions that still needed to be answered, and to make sure that whatever came out of this was really useful and was the most efficient use of those public resources. And this is just to show you the complexity of what they came up with. These different linked models of flow and reservoir operations, and how that flow moved through the system and caused the channel to meander, and what are the implications of that for salmon habitat and water temperature and cottonwood recruitment. So all of these models are linked ultimately into an output that compares different scenarios and goes into an output that is color-coded and something that policymakers can look at. And don't actually ask me too many questions about this, because I don't really know that much. I know the guys in California who are doing this, and I know what they're trying to do, and they're going to be releasing it in the next couple months. It's still in development. But I know that the ultimate goal is it's going to be a decision support system that will allow policymakers to look at the implications of different ways of managing the system. And again, because in California, you're not going to be able to just make a recommendation on expert judgment and have them start playing with the system. There's no slack in the system. So if you're going to suggest that they operate Shasta Dam differently, you're going to have to really back it up. You're going to have to say, we know you can do it, and we know it's going to produce these results. And that's where this type of approach is needed. But as I was saying, I think that the best way to look at it is as a sequential approach, so that you don't necessarily jump to level 3 if you don't really need it. If you're in a system that doesn't have as much complexity, or doesn't have, the stakes aren't quite as high, there's a little more slack in the system, maybe you should do an expert panel approach as a first cut, save those resources, and then use them very judiciously as uncertainties arise. So match your level of science to your level of uncertainty, because just looking at this order of magnitude in terms of the resources required, the Nature Conservancy has done this expert panel approach several times for under $100,000 for each river, whereas that Sacramento River example was $1.5 million. So they're very different orders of magnitude. And then just to harp on this point, but this idea of adaptive refinement being very important. And actually, from a logistics standpoint, it's extremely difficult to do, because it's hard to get agencies sometimes to fund ongoing monitoring, and so it requires a sustainable budget that can be very difficult to secure. So we're not being naive about this. We recommend it, but we realize that it's very hard for different places to do that. And in the interest of time, I'm just going to actually just move through this. This just explains what I just explained. Okay, so progress to date. These are various rivers where the Nature Conservancy and others have defined environmental flows. And that looks nice, until then you see that there really are an awful lot of rivers, and this is just the U.S., of course. If you scale back to the globe, it would look even more daunting. There would be the proportion of places that have had flow recommendations to the rest of the rivers that have not is tiny. So the key is trying to achieve scale, trying to achieve this at scale. And I'm going to talk about a couple examples of how these processes can be integrated into policy to try and achieve the necessary scale. And I'm going to talk about something about setting regional standards, about partnerships, and certification. 3 very different approaches. So regional environmental flow standards. The need is there because the processes that lead to hydrological alteration are much more widespread, and they far outpace our ability to look at them river by river. So there is need for some sort of regional approach that can be incorporated, for example, into statewide policy. And that regional approach could be at the level of a state or a large river basin or an ecoregion, but it's something that could actually be translated into state policy. And the example that the Nature Conservancy is working on is called the Ecological Limits of Hydrological Alteration, or ELOHA. And ELOHA is a very involved process, and this is also something that's most of what I'm talking about is actually kind of under development. So this is under development, and it's being tried in a few states. But just the gist of this slide is just to realize that there's a scientific process that is in the blue and the green, and there is a social process in the red, and these are interacting. And the scientific process has a hydrological database that draws on existing gauges of actual existing hydrological data, and then also models that will allow you to extend and extrapolate what you know about the hydrology to other river systems, so places that don't have gauges. And I think I heard that a group called Hydrological is actually trying to do this for North Carolina, to develop an oasis model, a type of hydrological model for basins throughout North Carolina. Then, when you have this hydrological database, you can do an analysis and to separate your rivers and streams into classifications or types. And so, from that point forward, you're now working at the level of a river type rather than an individual river, and that's where the economies of scale come in. Then you determine the degree of hydrological alteration at the various locations, and then develop flow ecology response curves for each river type. And I'll hit on those real quickly. So this is a river classification that was done for Michigan. So just looking at different river types like groundwater driven, runoff driven. So rivers that can basically be grouped together with similar hydrology, and you begin to make some assumptions, but similar ecosystems and therefore similar environmental flow needs. You begin to look at the degree of hydrological alteration at different points of interest, different reaches and rivers of interest there, and that gives you a picture of how things have been altered across the landscape, but also it helps you guide your subsequent research or data collection to make sure that you're looking at a full range of everything from reference sites that have not been altered to highly altered sites. And that's because really the heart of this is these flow ecology response curves, where with increasing hydrological alteration, you have a decline in ecological conditions, ranging from very low alteration, basically having natural processes and structure and functions, to highly altered, where you have something that does not really function like a natural river anymore. And that's a hypothetical one. This is one that shows, this is from Georgia, and actually, so this is where you have an increase in the amount of water that was permitted to be withdrawn from the river during the low flows, and the number of species that are called habitat specialists. So these are species that have very specific requirements for habitat or flow, as opposed to generalists that can kind of live in a broad range of places. And you see that as the amount of water extracted increases, these habitat specialists begin to drop out. So that's just an example of a flow ecology response curve that could be used in this process to begin to analyze how a given river type would respond to hydrological alteration. And then the social process then is, so setting aside those flow ecology response curves, the social process then needs to decide for these different river types and locations, what is the desired condition? Not every river is going to be maintained as if it was in a national park. You're going to have rivers that are, working rivers, and rivers that are kind of just average conditions. But that's a social decision. That's a value-based decision. And so that's something that goes through the political and social process to decide what are your ultimate goals? What kind of conditions are you striving for in different river systems? Then you can make the linkage between those flow ecology response curves and your objectives to develop flow standards that will allow you to achieve those conditions, and then implement, monitor, and refine. This is an example of I believe EPA came up with these, but the different stream classes, just focus on the left. They just broke streams into special value streams, typical streams, and working streams. It's just a simplistic approach, but you would have different objectives for these different types of streams. And so therefore different environmental flow standards to achieve those objectives. And this would be an example where your proportion of flow, this is just more of a conceptual approach, but just some type of flow characteristics that is being altered as you move across here. And then some sort of fish response that is declining in response to that alteration. And you pick these limits of how much alteration you will accept for different classes of streams. And then that allows you to translate that to a flow standard, which then could be translated into something that you would work with water managers to look at, in terms of granting new permits or reservoir operations or amount of water that's extracted. And this is where the real nexus, the nexus of this with state policy is the real challenge of how to incorporate a system that looks at a range of flows and environmental flow values across the whole state and incorporates that into state policy. Okay, another way of trying to scale up is that we're doing is working with the Army Corps of Engineers and other partners. And I talked about the Savannah River before, and I also referenced the Willamette River before. But this is something that we're doing on 9 river basins across the country. It's called the Sustainable Rivers Project, and we're collaborating with the Army Corps of Engineers on this. And part of the reason is, if you look, those are just some of the sites, but all these red triangles where the Army Corps of Engineers has dams, and the highlighted blue rivers are places that the Nature Conservancy has identified as priority aquatic ecosystems. So there's a huge overlap between where the Corps has dams and where the Nature Conservancy is trying to protect. So clearly, if we can come up with a way for the Army Corps to change the way they do business and the way they approach their reservoir operations at a large scale, that will reap much bigger benefits than just simply working at these 9 sites. So we've tried to work with the Corps of Engineers to develop this relationship to ultimately, ideally, have them incorporate these concepts more fully into their management everywhere, not just at the demonstration sites. And so far we've been doing joint trainings and conferences. We've developed some software together, software that their managers and operators use. But in the future, we want to maybe take that ELOHA concept, setting a regional flow standard, and have them do it at the district level, which is a major portion of the U.S. Do it at a district level rather than at a single dam level, or working into the engineering guidance manuals and policies that reservoir operators read and depend upon. If we get updates and revisions to those, and we're working on that, then there will be information in there about managing reservoirs for environmental flows. And then ultimately, the goal is that they will be integrating the thought process and the implementation of environmental flows into all aspects of dam management. And then finally, and I want to leave a little time for questions, so I'm sorry I'm going a little bit quickly. Thinking about hydropower. And the reason that the Nature Conservancy is trying to work with hydropower is that while much of the world, like Europe and North America, has fairly fully developed its hydropower potential, and there won't be that much more additional hydropower being developed, other parts of the world, like South America, Asia, and Africa, have developed relatively little of their hydropower potential. And if you look, this slide is showing the dark colors are the highest species richness of fish. So what is an interesting overlap is you've got the Mekong, the Amazon, the Congo. These are the places that also have had the least fragmentation and have the most hydropower potential left to be developed. And then this reiterates the same thing. This is where hydropower is going in the future, where the next increment of hydropower will be built. It's in those basins that are either moderately to lightly fragmented currently. And this just shows that the future of hydropower, or different scenarios for the future of hydropower. The installed capacity currently is 740 gigawatts worldwide. And it's estimated by various sources that there's about double that still that could be developed in terms of economically feasible hydropower. 120 of which is under construction, and 445 is under fairly immediate planning processes. So these two together are approaching what's installed already. And hydropower proponents are saying that we probably will build 1,500. We will double our current capacity. And then even the World Wildlife Fund, WWF, they're estimating that they came up with a scenario called Climate Solutions of how they think that we could achieve a more carbon neutral world. And they even said that they acknowledged that 250 gigawatts of hydropower probably could be done in a more sustainable manner. And if I didn't talk about it before, I mean, the reason to be concerned about hydropower in terms of its effects on rivers is that it can have a very, very severe effect on river ecosystems and on the ecosystem services that these rivers provide to downstream communities. And so it's been a major point of contention when dams are being proposed and built. The people who are trying to conserve the biodiversity of those rivers and the downstream communities and also upstream communities that might be flooded by the reservoir. So there's a lot at stake when these are being built. And what I would say is that even if you take WWF's estimate as a low and somewhere in that 1,500 as a high, there will be a huge increment of new hydropower built under any scenario. It's something probably close to what is already installed. And so therefore, it is imperative that organizations work with this process to ensure that this next increment of hydropower that's built is done as sustainably as possible in terms of its effect on river systems. And one of my colleagues likes to point out that hydropower is very appealing from a climate standpoint, as it's a low carbon source of energy. But what he suggests is that you shouldn't solve one environmental problem on the back of another environmental issue. And so that's why we're suggesting to take a very contemplative approach to the next increment of hydropower. So there will be a large increment built. It can have dramatic impacts on aquatic ecosystems. Most of the new hydropower that we've built will be built in areas with the greatest aquatic biodiversity. And one thing that we're looking into is this concept of certifying sustainable hydropower. And this requires working at very large spatial scales to be truly sustainable. And the point I'm trying to make is that working at the level of certifying an individual dam, there's only so much you can do in an individual dam. It needs to be done at a larger spatial scale, like a river basin. And that's because environmental flows at a single dam, you can change the daily and seasonal flow patterns, and you can affect temperature and water quality and other things, but you cannot affect generally migration barriers and other fragmentation that dams have for fish and other species. There are also barriers for sediment transport. So the downstream below the dam is often sediment starved, or the sediment regime has been changed, which has big consequences for the physical habitat. And then also peaking, which is when a reservoir is operated for major daily fluctuations to meet peak demand. And that is hydropower is often built specifically to provide peaking power, because it is very good at providing peaking power. But there's not much you can do to mitigate that. So the only way to mitigate that is to look at a basin scale and to try and help choose where dams should go and where dams should not go. And also how to link mitigation with mitigation not just downstream of a dam, but linking protection of one basin for development of another basin, which will allow all these processes that you can address through environmental flows, like sediment, like fish migration, to still be occurring in sufficient amounts in that basin. And so therefore it's kind of looking at some of those rivers as those will become the hard-working rivers, and then other rivers will be the protection rivers. And so at a basin scale, you can try and preserve the aquatic biodiversity and the ecosystem services, even as you're developing that hydropower. And this shows something that the Nature Conservancy did in the Yangtze Basin in China as a first step in this process, looking at different ecosystem types. And now we're currently working with the Three Gorges Dam Company to try and translate this into influencing some of their dam siting and operations. And real quick, just to illustrate what you can accomplish at scale, this is not looking at future dams, but looking at existing dams. This is the Penobscot River in Maine. It's a big river system, maybe about a quarter of all of Maine's land area. It has just a bunch of hydropower dams up and down the river. And a whole variety of agency and environmental group partners worked with the utility that had purchased all these dams to try and come up with a better way of managing it as a system. So what they did is they looked at this shows the amount of energy generated at each facility, and they looked at this map and they thought, let's move this generating capacity around in different ways, and they did move it around, and you see that several places get a lot bigger in terms of the amount of energy they're producing, and some places disappear. But the before and after is essentially it's unchanged. essentially the same exact amount of energy. But the difference, the ecological consequence of that, the shading here is places where anadromous fish like shad and salmon have access. On the left, extremely limited access, with almost the entire basin is inaccessible. But by shifting that type of flow around, shifting the energy production around, and where dams are located and where dams aren't located, you can see they open up almost the whole basin. Okay. Oh, I was hitting mute, that's why. Okay, so shifts up almost gets the whole basin accessible to fish. And they did that by removing several of the dams and by providing better fish passage at several of the dams and by shifting the key energy production to other dams that had less effect on passage for fish. So this is a slide of showing, this is a visualization of what that river reach will look like. And the concept here that I think can apply to thinking about future hydropower development is, let's say you had this basin and you were thinking about planning hydropower in the future. It was a completely undeveloped basin. Now, I already showed you that those two scenarios produce the same amount of energy. So wouldn't you rather come up with this scenario first rather than that scenario if they are energy equivalent? And so that's what we're really proposing, is that in places that where new hydropower is going in, and maybe it can't always be this dramatic, but let's look for ways of shifting that around and emphasizing hydropower in some sections and emphasizing passage and other biodiversity and ecosystem service values in other places to get this outcome rather than doing that outcome and a century later redoing it. And I'll just wrap up, say that we're trying to do this through certification, and you've heard of like the Forest Stewardship Council, FSC, for certified timber, and there's a whole range of certifications out there. But we're just beginning to pursue this. There's not even that much to say about it, other than that we are trying to work with groups like the International Hydropower Association on their assessment protocols and trying to move towards actual certification of hydropower as being more sustainable or less sustainable. But the real key is how to do that, not at the level of a single dam, but how to do that at the level of a whole basin. And that truly is the challenge. And so with that, I think I will just wrap up and just say that the challenges, the scale of the challenges that we're facing in terms of maintaining aquatic ecosystems and ecosystem services is immense. And the scale of other challenges is immense. There's something on the order of 1 billion people in the world that lack access to clean water, and even more that lack access to adequate sanitation. And throughout huge portions of the world, people lack electricity. And these are just fundamental things that people lack. And so clearly, there's going to be further water management and dam building. But also, as I showed before, aquatic ecosystems and the services they provide are really on the ropes. And so the challenges are immense, and so therefore the scale at which we try and address solutions has to be equal to those challenges. Thank you.